Buenas tardes a todos. Bienvenidos a este ciclo de conferencias que organiza la Fundación BBVA y que dirige la profesora Ana Chúcarro. Tenemos hoy al profesor Kip Thorne, que va a inaugurar este ciclo. Y antes de comenzar, me gustaría anunciarles la segunda conferencia de este ciclo, antes de que haya tenido lugar la primera todavía, que tendrá lugar el día 11 de abril, a esta misma hora, en esta misma sala. La impartirá el profesor James Cronin de la Universidad de Chicago y el título es Rayos cósmicos, un siglo de historia y la investigación actual. El título de este ciclo de conferencias, La ciencia del cosmos, la ciencia en el cosmos, hace referencia al doble papel que desempeña el universo en la ciencia que estamos desarrollando hoy en día. Por un lado, el universo, como no, es un objeto de estudio per se. Y cuando hacemos ciencia del cosmos, lo que queremos saber es cuándo se formó el universo, cómo se formó, qué condiciones se dieron en su origen, cómo evoluciona, qué contiene, de qué está hecho, qué leyes lo gobiernan, en fin, que lo queremos saber todo sobre el universo. Lo que pasa es que esta es una tarea posiblemente tan grande como el propio universo y nuestros objetivos necesariamente pues, tienen que ser más modestos. Pero nunca debemos perder la idea de que queremos conocer ese universo, cómo se comporta, etc. En este sentido es por lo que hablamos de la ciencia del cosmos. Pero por otro lado, el cosmos nos sirve como laboratorio privilegiado en el que se dan condiciones extremas que son a menudo imposibles de recrear en la Tierra. La ciencia que se puede hacer en el cosmos puede alcanzar regímenes extraordinarios, cuyo estudio es accesible mediante instrumentos de observación astrofísica y cosmológica. Por ejemplo, tenemos bajísimas temperaturas en regiones extensas. También tenemos altísimos vacíos. En su origen, por ejemplo, en los procesos astrofísicos también, en los rayos cósmicos, tienen lugar altísimas energías y en algunas situaciones altísimas densidades que ni siquiera en los más potentes aceleradores que podamos construir en la Tierra podemos soñar con conseguir. En el cosmos también encontramos campos gravitatorios muy intensos, como los que se dan, por ejemplo, en las estrellas de neutrones. En las estrellas de neutrones, los electrones literalmente se incrustan en los protones para formar los neutrones debido al campo gravitatorio. O en los agujeros negros, de los cuales el profesor Thorne nos va a hablar hoy y de cuyo campo gravitatorio pues ni siquiera la luz puede escapar. En resumen, la ciencia en el cosmos lo que nos permite es llegar a los límites de validez de nuestras leyes y de nuestras teorías, e incluso sobrepasarlos, abriendo ante nosotros el paraíso de lo desconocido. Es para mí hoy un inmenso placer, presentar al profesor Thorne para inaugurar este ciclo de conferencias organizado por la Fundación BBVA, a quien conocí en mis tiempos de estudiante a través de su libro negro, Gravitation, que escribió en colaboración con los profesores Charles Misner y John Wheeler. Y es negro, supongo que no por el contenido de magia negra ni nada por el estilo, sino realmente por el color de sus tapas y quizá también por el tamaño, puesto que es un libro inmenso, tanto en calidad como en cantidad. Para los que lo conocen, sin duda saben de qué hablo. El profesor Kip Thorne nació en el estado de Utah en el año 40, obtuvo el grado de licenciado en Caltech, en el Instituto Tecnológico de California, en el año 62 y se doctoró en la Universidad de Princeton en el año 65 bajo la supervisión del profesor John Wheeler. Después ya regresó a Caltech en el año 67 y había permanecido hasta hoy. Desde el año 91 es titular de la cátedra Feynman de Física Teórica y es emérito desde el año 2009. Y en esa fecha lo que pasó es que decidió continuar con sus investigaciones, por un lado, eso sí, pero por otro lado dedicar también una buena parte de su tiempo a otras actividades, como por ejemplo la de escritor y, como no, también se ha ido a hacer cine. Ha recibido numerosos premios de varias academias y sociedades científicas de todo el mundo, tanto por sus logros y su brillante carrera científica como por su labor divulgadora. Sus contribuciones científicas no son menos numerosas, abarcan múltiples aspectos de la física gravitatoria, desde los agujeros negros hasta las ondas gravitatorias, como el propio título de su charla indica. Es cofundador de LIGO, que es el acrónimo de Observatorio de Ondas Gravitatorias mediante Interferometría Láser. Ha contribuido seminalmente en muchos aspectos de la física gravitacional, desde estudios sobre la comprobación experimental de la relatividad general, la física de agujeros negros, ahí incluyendo aspectos clásicos y también análisis termodinámicos que necesariamente incluyen efectos cuánticos, en la física que subyace los viajes del tiempo, hacia el pasado, ¿no? Hacia el futuro pues viajamos cotidianamente y parece que es más fácil. El problema suele ser viajar hacia el pasado. Y como muestra numérica de su prolífica carrera, pues quizá baste con decir que ha dirigido más de 50 tesis doctorales y ha publicado un sinfín de artículos, más de 170 artículos científicos y al menos media centena de artículos de divulgación. En fin, no me extiendo más, han venido ustedes aquí a escuchar al profesor Thorne y no a mí, así que yo creo que lo mejor es que le deje hablar. Profesor Thorne, muchas gracias por estar aquí hoy con nosotros, es su turno. Thanks very much for being here, so it's your time now.
Gracias, muy gracias. I apologize that I do not speak Spanish, but you will have to bear with me and with a translation for those of you who wish to have it. We have an excellent translator. By the warped side of the universe, I mean phenomena and objects that are made from warped space and warped time. The typical example of an object on the warped side of the universe is a black hole. This black hole appears to have a circumference of about 3 meters. And so you would expect that the diameter through the black hole would be 3 meters divided by pi, or 1 meter. But in fact, the diameter is far larger than 1 meter. And you might ask, how is that possible? And I will give you a simple example to explain. Suppose that I take a rubber sheet, a child's trampoline. I put it high on stilts, on sticks, and I put a very dense rock, a very heavy rock in the center, so it bends the rubber down in this manner. Suppose now that I am an ant, but I'm a blind ant. I can't see what is going on, but I have studied engineering, and so I believe that I would like to study the universe that I'm in. So I measure the circumference around this region, and then I go to measure the diameter, and I walk a very long distance and find the diameter is large compared to the circumference. And I say to myself, obviously, I live in a universe that is warped. The space is warped. It does not obey the geometry of Euclid. And now, precisely the same diagram is used to describe what happens in a black hole. In the black hole, the surface here is, in fact, an equatorial slice, a surface through the black hole. It's embedded then in a higher dimensional flat space, and we see that it is bent down in this higher dimensional space. So we look in from the outside in this hyperspace, and we see that that around the black hole space is highly warped. The rock at the center has been replaced by a singularity, a region where gravity is infinitely strong. Now, the black hole has the property that if you fall into the black hole, you can never come out, and signals that you send can never come out. So this is a drawing of me falling into the black hole, sending signals with a microwave transmitter. When I fall through the horizon, after that I am pulled toward the singularity, and the signals are pulled toward the singularity. They cannot get out. The reason this happens is because of warped time around the black hole. In addition to this warping of space, there is this warping of time. If you go down near the surface of the black hole, you find that time slows down there. If this is the black hole, I go down in a rocket and I hover, I stay just above the horizon of the black hole for 1 day, and then return to Earth. 1 million years may have passed on Earth. Time slows to a halt. It doesn't move at all at the horizon, the surface of the black hole. Inside the black hole, you cannot remain at the horizon. Inside the black hole, time flows toward the center. You might think that this was a direction of space from the horizon to the center, but it's a direction of time. Time is flowing in that direction. Nothing can go backward against the flow of time, and that is why nothing can get out of the black hole, because the flow of time is from the horizon down to the singularity. Black holes also spin, and as they spin, they drag space into motion around them, like air in a tornado or water in a whirlpool. And this whirling motion of space is fast, as indicated by these arrows near the horizon, slower farther away. Again, similar to a tornado, fast motion of air near the core of the tornado, slower farther away. The singularity at the center of the black hole is very interesting. According to theory, and everything I'm telling you now is theory. I will talk about observing this in a few minutes. But according to theory, if I fall into the singularity, then as I near the singularity, the warped space and time there will stretch me from my head to my feet and squeeze me from the sides, then stretch me from the sides and squeeze me from head to foot. This stretch and squeeze and stretch occurs faster and faster in a chaotic pattern. In fact, a pattern governed by a mathematical map, to use technical terms, that is a chaotic map. Ultimately, my body is completely destroyed, and then the atoms from which my body are made are stretched and squeezed until they are destroyed, and everything is destroyed in the singularity, according to Einstein's laws of gravity, his laws of general relativity. But general relativity is not the entire set of laws of physics. There are also laws of quantum physics. And we now understand that at the center of the singularity, where everything seems to be destroyed, in fact, a new set of physical laws arises, the laws that are obtained by marrying or unifying general relativity with quantum theory, unifying the theory of warped space and time with the theory of quantum mechanics that governs atoms and molecules. These laws of quantum gravity, when we understand them more clearly, they will tell us what truly happens at this singularity, and also what truly happened in the singularity where the universe was born, in the Big Bang singularity. Now, there are other objects on the warped side of the universe, made from warped space and time rather than from matter. One is the Big Bang singularity itself. A second is the possibility of a naked singularity that is not inside a black hole. And I will talk about a bet that I have had with Stephen Hawking, whether you could make a naked singularity. Can you make a region that is governed by the laws of quantum gravity, where the gravitational forces appear to be infinitely strong, without having it hidden inside a singularity, inside a black hole? Our universe may in fact be a membrane, a surface, we call it a brain in English, in a higher dimensional hyperspace, which physicists call the bulk. So this is a surface in a higher dimensional space. The surface might be our universe. And this may in fact be the very nature of our universe. It lives in a higher dimensional space. Wormholes are a possibility according to the laws of general relativity. If I have a wormhole, I may climb into this wormhole here and come out in California. I will talk briefly about wormholes. Cosmic strings. A cosmic string is an object that may have been created in the birth of the universe by taking a fundamental string, as we have in string theory, a fundamental string, and having it be expanded to cosmic scale. How? By what we call the inflation of the universe at the very beginning. And such a cosmic string has the property, the circumference around it is smaller than pi times its diameter. I will return to cosmic strings at the end of the lecture. And gravitational waves. These are ripples in the fabric or the geometry of space and time that can be created by all of these objects and travel out to us, to Earth, bringing us information about the other objects on the warped side of the universe. Gravitational waves are made from the same thing as wormholes and singularities and black holes They're made from warped space and warped time. So they are the ideal tool for observing objects on the warped side of the universe. So these are a number of examples of things that we have speculated about, physicists have speculated about on the warped side of the universe, which are real, and what else might there be on the warped side of the universe. We have a set of tools for answering these questions. The first is theory, equations done on paper or by computers by people like Einstein and Stephen Hawking. The second is numerical simulations on computers. This is a new tool. Only in the last several years have we had this tool and been able to use it to explore objects on the warped side of the universe. Radio telescopes, optical telescopes, other kinds of electromagnetic telescopes have told us that there are black holes in the universe, but they have not shown us yet very much about the black hole's properties. And then gravitational waves that can bring us pictures of the warped side of the universe. Numerical simulations and gravitational waves are new tools. I have devoted much of my career to trying to make these tools become mature tools that we can use to explore the warped side of the universe. And so I will talk about these new tools and what we are learning about the warped side. So let me begin with numerical simulations. We call this field numerical relativity. It is the business of using a computer to solve Einstein's relativity equations in situations where we are too stupid, too dumb to be able to solve them ourselves by pencil and paper. Numerical relativity has been under development since the 1960s. It's a long time, a half a century since this field began, but only in the last 4 years has there been real success. It has taken nearly half a century to develop the techniques to solve Einstein's equations on computers, and for the technology of computers to become good enough that we would be able to use that technology to solve Einstein's equations fast enough to get interesting results. Perhaps the most interesting problem that my colleagues and I have been trying to understand using computers is what happens when two black holes orbit around each other, spiral together, collide, and merge. We do know from simple arguments, simple analytical arguments with pencil and paper, some things about this. First, we know that the power output that's coming out from this collision is big. During the collision, there is more power comes out than the total power from all of the stars in the universe put together, 10,000 times more. The luminosity or power of colliding black holes is 10,000 universe luminosities. I mean, this is unbelievable. It's for a short time during the collision, but this is the most violent process that has occurred ever in the universe, with the exception of the Big Bang itself. And no electromagnetic waves are emitted in this process. All of this power comes out in gravitational waves. Why? Because to make electromagnetic waves, to make light or radio waves, you must have electrical charges that oscillate, that move. But the black hole is not made of matter. There are no charges to oscillate. The black hole is made from warped space and warped time, and so it can't produce electromagnetic waves. Instead, it produces these gravitational waves that are made from the same thing as the black hole. These gravitational waves come out to us, and they should bring us a detailed picture of what happens when the black holes collide. The picture is contained in gravitational wave form that I will talk about in a few minutes. It's the shape of the gravitational wave that comes past. It carries information about the collision in the same way that the sound from a symphony orchestra contains information both about the composer the mood of the composer when the composer made wrote this symphonic piece, and information about what instruments are being played, a violin, an oboe, and so forth. In the same way, the gravitational wave shapes carry detailed information about how space and time are behaving when black holes collide. And this, for me, is a very exciting possibility, because each black hole spins, and as it spins, it drags space into whirlpool motion. So we have two whirlpools, or two tornadoes, spinning. And as the black holes orbit around each other, that orbital motion also drags space into a whirling vortex, a whirlpool motion. And so we have two tornadoes contained in a third larger tornado. And these tornadoes are coming together and crashing together, and we want to know what happens when the tornadoes are made from whirling space and warped time. This is perhaps the most profound way to explore the nature of space and time that we have today, is to explore how the warped space and time behave in these collisions of whirling space of two black holes. I'm going to show you a movie from Numerical Simulations, Numerical Relativity, an example. This movie is of two black holes spiraling together and colliding, but these black holes are not spinning, so they're not very interesting. Nevertheless, it is impressive what happens in this movie for the non-spinning case. You're going to see three things in this movie. At the top, you will see two black holes. One is here, the other is off the screen. These are black spheres. This is how the black hole would look if you looked at it in our universe with a blue sky behind. Of course, you really have stars behind, but in this simulation, we just show a blue sky behind. Down here is a picture of the collision as seen by somebody looking in on our universe from a higher dimension. Like our universe is a sheet, a two-dimensional sheet. The black hole is bent down, space is warped down there, as I showed you before. The arrows show space dragged into motion, but not a whirlpool motion, not a circulating motion, because these black holes are not spinning. And down here you see the gravitational wave form, the shape of the gravitational wave that's emitted. And as the movie goes, here you see where we are in the waveform. We see the two black holes as in our universe going around each other. We see the black holes looking in from the outside. The colors are encoding the warping of time. Now I jumped way over to the end because the end spiral is boring. Now we will see the black holes collide, and I'll stop the movie while they collide so you can admire these colliding black holes. And now the final black hole vibrates a little and settles down. It has become a single black hole, but in that process, an enormous amount of power has come off in gravitational waves, which we will use to observe this. Now, spinning black holes are much more interesting, and for the next several minutes, I will tell you about results that have not yet been published. These are the newest and to me very exciting results from the simulations that are being done by a group at Caltech, my research group, the group led by Professor Saul Tucholsky at Cornell University, and a group that is led by Professor Harold Pfeiffer in Canada at the University of Toronto. What we have learned just very recently from a combination of simulations and theory is that not only does space whirl around a black hole, but there are guiding lines that stick out of the black hole that are very much like magnetic field lines. You know, the Earth has a magnetic field. Magnetic field lines reach out and around from the North Pole to the South Pole. These are like magnetic field lines, but they are the lines in curved empty space that control the whirling motion of space. We call these vortex lines. And these lines have the property that if you go in here and you are hanging above the black hole, suspended by a rope, that your feet are pulled into motion faster than your head. And so when you look down, you see your feet going around in a counterclockwise direction. But your feet look up at your head, which was going more slowly, so it looks like it's going in the opposite direction. But if you think about this, as seen from your feet, your head looks like it's going counterclockwise. So it turns out, sticking out of the north pole of the black hole, there are counterclockwise vortex lines that control this spinning space. Sticking out of the south pole, there are the opposite kinds of vortex lines that control the spinning space out of the south pole. So these are clockwise vortex lines. They put a clockwise twist on a person. These put a counterclockwise twist on a person. Here now are two black holes. This is from a movie that I will show you in a moment. Two black holes that are going to collide. They're moving toward each other. And this is the horizon of the black hole, but we have painted the horizon. Again, this is from a simulation. We have painted the horizon red in the region where these counterclockwise vortex lines come out. So where you see it red, space is whirling around in that direction. And where you see it blue, it's whirling around in the opposite direction. Space is whirling. And these black holes will collide and merge. And the wonderful thing we've discovered is when the black holes collide and merge, they place on the merged horizon. This is the boundary that you go inside here, you can never get out. They put on the merged horizon both of the vortexes from the first black hole and two vortexes from the second black hole. And if this is two black holes orbiting each other, there would be two more vortexes from the orbital motion put on here. But in this case, it's a head-on collision. And so there are four vortexes sticking out of the black hole. Black holes are not so simple as we thought they were. They have these interesting whirling space around them. So here is a movie, and you will watch what happens after the black holes collide and merge. So they're coming together, they raise a tide on each other. Now look, this was a blue vortex, now it's a red vortex. Now it's a blue vortex. Now it's a red vortex. Now it's blue. What's happening is that as soon as the vortexes see each other on the black hole's horizon, they don't like to have neighbors. And they slow each other down. So this vortex is going like that, and the neighbor slows it down, and then it overshoots and it goes back and goes the other direction. And it goes in one direction, then in the other direction, then in the first direction, and then the other direction. And what happens to the vortex lines? I don't have a good movie, but I have some snapshots, some pictures of what happens to the vortex lines. Each time these vortexes turn around their direction, these vortex lines come off the black hole because it's no longer spinning, and they connect up around to the other side of the black hole, and they make a smoke ring. This is very much like a smoke ring. It's a whirling donut or toroidal-shaped vortex with its vortex lines guiding it, controlling it. And this is from an oscillation where it turned around that occurred a little while ago. This was the next oscillation, and these vortex lines, they will make the next donut-shaped or toroidal-shaped vortex of whirling space. These travel out toward the Earth, and they become gravitational waves. It's rather remarkable. This is how a black hole makes its gravitational waves. If that's the special case where the black holes collide head-on. Now, if the black holes are orbiting around each other, then when they collide and merge, Their vortex lines reach out in spiral arms, like the spiral arms of a galaxy, and travel out in that way, becoming gravitational waves. And so each of these, this is a whirling space. The whirling becomes weaker farther away from the black hole, but this becomes the gravitational waves that we are seeking to detect on Earth. So this is an example of the wonderful new things we're learning about how warped space and warped time can behave. Let me show you the real power of the whirling motion of a black hole. Here is a picture of a black hole. It's spinning around the red axis. This is the north pole of the black hole. This is a star. It's a neutron star. The neutron star is orbiting around the black hole down in this plane. So it's not in the equatorial plane of the black hole is up there. The neutron star is orbiting in this plane. This neutron star is made from matter that is more dense than the nucleus of an atom. The neutron star has a size of about 20 kilometers diameter. It has more than the mass of the entire sun packed into that very small size. And it's orbiting around the black hole, spiraling together. It's going in closer and closer to the black hole, emitting gravitational waves as it goes. And the loss of energy from gravitational waves causes it to come in closer and closer to the black hole. And here is what happens. You see, it starts to be torn apart by the black hole, and then it's thrown up into the plane perpendicular to the black hole's spin. This black hole's whirling space has the power to take more than one solar mass of energy, of matter that's in the form of nuclear matter, and throw it up in the air, basically, into a different type of motion. This whirling space is so powerful it can do that, and that's the kind of whirlpool that we're dealing with in these vortexes around black holes. In this process, not only do we get gravitational waves out, when this is a neutron star being torn apart by the black hole, we also get gamma rays, very high energy photons, very high energy electromagnetic waves. We get neutrinos from nuclear processes in this nuclear matter. And so, at the present time, in the gravitational wave project that I will tell you about next, in LIGO, our gravitational wave project, we have built close collaborations with astronomers who are looking at the sky using these other kinds of radiation, gamma rays, neutrinos, also optical light and radio waves, and so that we can study the same objects at the same time. If what we have is two colliding black holes, there is no electromagnetic radiation. But if it's a black hole tearing a star apart, there are many other things to see with other kinds of radiation. So let me turn in the remainder of most of the rest of my lecture to gravitational waves as a tool for probing, for studying the warped side of the universe. This is a diagram of the kind of detector that my colleagues have built. I was involved in starting this project, but it's really the superb experimenters working on this project around the world who have made this happen successfully. And this is the kind of detector they have built. What a gravitational wave does when it arrives at Earth, it's very weak because it has traveled across the universe from its source. And it moves space, it stretches space back and forth in this direction and back and forth in that direction. If it propagates from me to you. It stretches in one direction, squeezes in the other. The next half cycle of oscillation, it stretches in this direction, squeezes in that direction. And things that ride freely on space, they are similarly stretched and squeezed. They're pushed back and forth with each other. What's really happening, if I may get more technical, is that inertial reference frames at this location and that location, they move back and forth relative to each other. And anything that tries to remain inertial, then to an object here and an object there that try to remain inertial, they move toward each other and away by very small amounts. So what we do is we hang by wires from an overhead support large mirrors, one mirror here, one there. As the gravitational wave goes by, it stretches the distance between these mirrors and then squeezes them together. We do the same thing along here, hang two mirrors. When this distance is being stretched, that distance is being squeezed, it's being reduced. And so we use a technique called laser interferometry to measure with laser beams the difference in this distance between the mirrors and that distance. We measure the stretching and squeezing. Now, the pattern of stretching and squeezing is the gravitational waveform that I spoke about. It carries the detailed information about the wave. And so the project that I have been working on with my colleagues at Cornell University and University of Toronto is to compute the gravitational waveforms from various sources. So we are building a dictionary of gravitational waveforms or shapes, so that when we see this waveform, we will know this is caused by two black holes. One black hole is spinning at a high speed. The other black hole is traveling around an orbit like this, and the orbit is turning, it's precessing. And so the detailed waveform tells us about the source. And so we will use these to translate the observational waves into pictures of what these black holes were doing. To go back to the detector, let me give you some numbers. The separation between these mirrors in our gravitational wave detector is 4 kilometers. The gravitational wave pushes the mirrors we expect for the sources that we believe we will see, pushes these mirrors back and forth by a fractional amount of 10 to the minus 21. This is a very small number, 0.20 zeros and a 1. The product of that gravitational wave strength with the separation 4 kilometers is 4 times 10 to the minus 16 centimeters. That is the motion of these mirrors with respect to each other. To be sure that what we are saying is really a gravitational wave, we must have a sensitivity much better than that, say 1 times 10 to the minus 16 centimeters. And that is the sensitivity of the instruments that the team I work with is achieving. Now, let me just remind you of what 10 to the minus 16 centimeters is. I begin with 1 centimeter. We all know 1 centimeter. At least in this country, you know 1 centimeter. Not. You divide it by 100, you have the thickness of a human hair. Divide by 100, you have the wavelength of the light that we use in our gravitational wave detectors. Divide by 10,000, you have the diameter of an atom. Divide by 100,000, you have the diameter of the nucleus of an atom. Divide by 1,000, you have the sensitivity, you have the motion that is produced by these gravitational waves, and that our team is now able to detect. It is very impressive. In fact, I wrote a textbook that I think you mentioned together with Misner and Wheeler in the 1970s, in which I wrote an exercise which says, it is proposed to detect gravitational waves by this method. Show that this is stupid. It will never succeed. And then 10 years later, I began to devote much of my life to helping make it succeed. So it looked impossible, but in fact, it is possible and it has been done. So we now have a network of 4 detectors, 2 in the US, 2 in Europe, of gravitational wave detectors. The ones in the US are called LIGO, the Laser Interferometer Gravitational Wave Observatory. This is the project that I helped start. We expect a 5th detector to join the network in Japan. The funding for this has just been given. And we hope to move one of our US detectors to West Australia, so that by about 2015, 2016, we will have an expanded network. Why do we want this network? These waves are very weak. They produce tiny, tiny motions, and you will not believe these motions when you see them unless you see the same kinds of motions in detectors that are widely separated, independent detectors. So for confidence that what you see is real. Also to extract the wave shape, the waveforms, it turns out we need a network. And to determine the direction to the source, we need a network. And so this is an international collaboration. LIGO is the piece of this international network that I'm involved with. Just give you some numbers. This is a collaboration now of 800 scientists at 75 institutions in 13 nations. It's headquartered at Caltech because we were the ones with MIT that started it. Spain is a very significant contributor, particularly to the analysis of the data from LIGO. These are the nations that are involved. This is our detector in Livingston, Louisiana. That was the detector in Hanford, Washington. And when we originally proposed to build LIGO, after nearly 20 years of research and development of the techniques and the technology, we said we will do it in 2 steps. We will build detectors, interferometers we call them. We will build interferometers that are at a sensitivity where we probably will not see anything, but we know we can build these. And then, having gotten experience with those first detectors, we will then improve them in a very large step so they have the sensitivity where we should see many, many gravitational waves. But if we're lucky, the first interferometers will see gravitational waves. So our first interferometers operated from 2005 to 2010 in 2 pieces, 1 piece for 2 years, and then we improved them a small amount, and then another segment of operations. With a capability to see black holes colliding out to a distance of 300 million light years. And at this distance, the number of black holes colliding that we might see is about 1 every 10 years at best, and probably less than that. And so, yes, we did not expect to see anything, but if we were lucky, we would. Nothing has been seen yet. We began installing the advanced detectors, the ones that should have big success. After having this experience, we began installing them last October, 6 months ago. And these advanced detectors, or interferometers, should begin operation about 2013, 2014, with gradually improving sensitivity. And they will, when they reach their design, they will see black holes colliding out to 4 billion light years. That's nearly across the entire universe. And we should see between 3 black hole collisions per day and 1 every 2 years, at the most pessimistic possible, 1 every 2 years. But most likely something like 1 a month or 1 a week is the most likely estimates. We will also watch black holes tear neutron stars apart. We'll watch neutron stars collide. We'll study the cores of things called supernova explosions, of gamma ray bursts, a number of other phenomena that we will study with these gravitational wave detectors. The advanced detectors, which we are now installing, are really remarkable because in them we measure the motion of these mirrors to a precision at which the mirrors behave according to the laws of quantum mechanics, not classical physics. We measure their motion with such high precision that we see fluctuations in the position of the mirrors that are due to the so-called uncertainty principle of quantum mechanics. For the first time, we will see objects that are the size of a human behave according to the laws of quantum physics. And this means that we must design the detectors to take account of this. We have built into these advanced detectors something called quantum non-demolition technology. This is a branch of the field of quantum information science, a new 21st century field that includes quantum computing, quantum cryptography, quantum communication, and quantum non-demolition experiments. And so that is built into these gravitational wave detectors. We also are planning a second kind of gravitational wave detector that will fly in space, 3 spacecraft that track each other with laser beams with separations of 5 million kilometers. These then are looking for gravitational waves where the wavelength, the distance between the crests and the troughs of the wavelengths are 10,000 times longer than LIGO will see. So the waves that this LISA, laser interferometer space antenna, the waves that this detector will see are like radio waves, if you think of LIGO, of the ground-based detectors, as being like light. And so we want to open up the very long wavelength window on the universe with gravitational waves to go hand in hand with the shorter waves that LIGO will see. And with these, we will see, for example, giant black holes in distant galaxies. The LISA, shown here in a sketch, is being tested in something called LISA Pathfinder. It will be a space flight in 2013 to test the technology. If that goes well, then the launch of LISA will be probably around 2022. So this is much more distant than advanced LIGO, which we are now installing, but very exciting. For example, with LISA, we will watch small black hole orbit around a large black hole, gradually spiraling in. And it turns out that, according to theory, the gravitational waves from this carry a full map of the warped space-time of the big black hole that the small black hole is experiencing as it goes around and around. So we will measure with very high precision the shape of space, the slowing of the flow of time as you near the horizon, the whirling motion of space due to the spin of the black hole. These will all be measured with exquisitely high, very high precision with LISA. Just some numbers. It will take, the size of LISA is about, LISA shown here is about the same as the size of the source. A black hole that weighs 1 million times what the sun weighs, with a small black hole 10 times the mass of the sun orbiting around it. The distance between LISA and the source may be 3 billion light years. And in the final year of the motion of the small black hole around the large hole, there will be 100,000 orbits in just the region that I'm showing. With 100,000 orbits, you get a very high precision picture of the big black hole. And what if the map that we get out is not that of a black hole? Then we may have discovered a new kind of phenomenon on the warped side of the universe, for example, a naked singularity. We will look to see what the maps look like. Are they the maps that we get out? Are they of black holes, or are they of something else, such as a naked singularity? A naked singularity, then, is a singularity like at the center of a black hole, where everything that falls in would be destroyed, but it's not hidden inside a black hole horizon. And so there's a question, can naked singularities really exist in our universe? The establishment, by which I mean people like Stephen Hawking, the most famous physicist in the world, they say probably not. Roger Penrose, another very famous physicist, has given us a cosmic censorship conjecture that all singularities except the Big Bang are hidden inside black holes. They're clothed by horizons. There are no naked singularities. And so a few years ago, John Preskill and I had a bet with Stephen Hawking. It says, whereas Stephen Hawking firmly believes that naked singularities are an anathema, that they should be prohibited by the laws of classical physics, whereas Preskill and Thorne regard them as interesting quantum gravity objects that might exist without horizons. Therefore, we will take a bet. These were Hawking's words to protect his side of the bet. And the loser will reward the winner with clothing to cover the winner's nakedness, clothing to be embroidered with a suitable conceding message. We won the bet. Hawking conceded, not graciously. This is the piece of clothing he gave us. with a young woman hiding her body by a towel that says, "Nature abhors a naked singularity." In other words, Hawking agreed that if you were a very advanced civilization, you could make a naked singularity artificially, but he maintains they could never occur naturally in the real universe. And so we have a new bet about that. And let me just say that the thing that convinced him that we were right, that you could make, if you were a very advanced civilization, you could make a naked singularity, was simulations on a computer of the in-spiral of waves that nearly make a black hole, but not quite. Very finely tuned. The advanced civilization that does this, that sends waves in and makes the naked singularity from imploding waves, has to do this very carefully, and it could never occur in nature. And so we have a new bet whether or not there can be big, long-lived naked singularities, and we will answer this by looking for them with gravitational wave detectors. Just a few words about wormholes, and then I will come to the closing moments of my talk. A wormhole would look like this if you had one. I might have a mouth in my office here in Pasadena, and there might be a mouth sitting outdoors here in Spain. If you look through the mouth in the office, you would see what's going on outdoors in Spain. If you sit here in Spain outdoors and look into this wormhole, you see me in my office. Well, this isn't really me because I lifted this from a photograph of somebody else. But the wormhole acts like a light pipe. It brings a picture of what's at the other mouth out through this mouth. The mouth looks like, sort of like a crystal ball. And as I indicated before, I could crawl into this mouth and come out of that mouth. Now you might ask, how is such a thing possible? And the answer is, it is allowed by Einstein's laws of warp space. And the word wormhole comes from this analogy. We can think of our universe as being like the surface of this apple. A worm has eaten a hole through it from one side to the other. I'll now flatten the apple so the distance through the apple, through this wormhole, is quite short. But it's still, you have to go around it a much larger distance if you go around the outside. So you have a choice. If you want to go from here to there, you can go through the wormhole or you can go around the outside. The region inside the wormhole is not part of our universe. It's a higher dimensional space. And so this is what wormholes are like. They are ideal for fast interstellar travel if you have the right technology to build them. If they are allowed by the laws of nature, then the technology is as far beyond us as space travel is beyond the ability of an amoeba, of a very small microscopic objects. It's impossible for us. But there are big issues. How do you make wormholes? We don't know whether they can even be made. How do you hold them open? Wormholes tend to collapse before you can travel through them. Can they exist naturally? Almost certainly not. And so we don't know today whether or not wormholes are actually allowed in the real universe. I'm going to conclude with a brief description of what I see as the most exciting subject for the next 40 years in physics, and that is to study the initial 1 second of the universe's life and, in fact, watch the universe be born. And the way that we expect to do this is with gravitational waves. If we look out in the sky, we see cosmic microwaves, electromagnetic waves, coming to us from the Big Bang. These waves are produced when the universe was very young and bring us a picture of the universe at the time, in fact, when the universe was roughly 100,000 years. Well, really 380,000 years, but to astronomical accuracy, roughly 100,000 years. And these photons, electromagnetic waves, cannot bring us a picture of the universe any earlier than that because the universe was so hot and so dense that photons could not travel in the very early universe. And they would be created, they would be absorbed, they would lose all their information. The new ones would be created, would be absorbed, lose all their information. Neutrinos can bring us a picture. These are fundamental particles also that are very penetrating. They could bring us a picture of the universe at age 1 second. But earlier than that, they are absorbed and could not have brought us a picture of earlier. Gravitational waves are the only form of radiation that penetrates so strongly through matter that it could travel from the birth of the universe to us today and bring us a picture of the birth, or of whatever went on in the first 1 second of the life of the universe. And there, we think, was a lot of violence in the first second of the universe, and this is what I would like to study with gravitational waves in the coming several decades. First is the Big Bang Singularity itself, and the inflationary expansion of the universe immediately after the Big Bang. Second are these cosmic strings that I mentioned that we think may have been produced by enlarging fundamental strings from string theory during the inflationary expansion of the universe. This is a simulation by Ken Olam at Tufts University of a cosmic string that has a kink on it, a bend in it, and it throws off gravitational waves as this bend moves. How would you get a bend? Well, strings would run into each other, collide, and when they collide, with high probability, they reconnect. And so you wind up with a bend in this string and a bend in that string when they reconnect. And gravitational waves are the ideal tool for searching for these things and thereby testing string theory. When the universe was 10 to the minus 12 seconds old, 1/1,000,000th of a second old, theory says that at that point the electromagnetic force was born and the weak nuclear force was born. Earlier than that, these forces were unified, and the unified force came apart, and the laws of physics as we know them came into being at that very early time. And this may have happened in bubbles like water droplets condensing in the sky. And if so, then this is called a first-order phase transition. If so, then the region where the forces have separated, the new laws of physics are occurring, is inside these bubbles, and these bubbles will expand at nearly the speed of light, collide, and produce gravitational waves in the collision. And those gravitational waves are predicted today to have the right wavelength to be seen by LISA. And finally, our universe might have been born as a membrane, or brain, in higher dimensions that was all crinkled up like this sheet of paper. And when the universe discovers that there is a bend in this membrane between here and there, there's a large tension in the membrane, like in a piece of rubber, and it quickly straightens out and vibrates with very large amplitude vibration. And those vibrations are seen by us living in the brain as gravitational waves. And so this is an example of the kind of surprise that gravitational waves could bring to us. It's very speculative, but it is a possibility. So let me conclude. We are actually very ignorant about the warped side of the universe. We don't know the answers yet to these questions. Does a black hole have the precise shapes of warping that general relativity predicts? What happens when black holes collide? We are beginning to learn the answer now. The Big Bang Singularity, what were the details of the birth of the universe? What came before the Big Bang, if anything? Was there a before? Is our universe truly a membrane in a higher dimensional space? What other objects reside on the warped side of the universe? Singularities, what are their structures? What do the laws of quantum gravity say about them? The Big Bang Singularity, the singularity in the core of the black hole, how do they behave? The answers are going to come from gravitational wave observations and numerical simulations together with fundamental theory. And so this is really, for me, a very exciting period that I have been waiting for, when we would have the tools to answer these kinds of questions. We have them now with the numerical simulations. We are coming close with the laws of quantum gravity with several different approaches that are being worked on by different teams of people, string theory, loop quantum gravity, and we are coming close with gravitational wave detection. We should be there with gravitational wave detection by 2016, possibly by 2014 with the advanced LIGO detectors. So it's truly for me a really exciting time to be doing physics. Thank you.